All right, well, good Friday morning. Today's plan is we're going to talk about improper integrals. They're called improper because something's funky with their bounds, and we'll talk about that. But that's the plan today. But of course, as always, I'm willing to talk a little bit about homework. If there are any questions you guys have, anything you'd like to look at. Wow, color me impressed. Oh, there it is. Lexi got it in. I was about to say, are you kidding me? No questions. So 10, 15, and 19 from 3.4. I'm quite certain we're not going to do all of them, but we'll at least get them all set up. All right, well, let me hop over there. Okay, then Rigney just threw in 3.3, 16, or 17. All right. Let's start with the 3, 3. All right, so 16 or 17, I'll pick 17. All right, so solve the initial value problem for y as a function of x. Okay, so remember initial value problems, what they mean. They actually let you figure out what the c is, right? That's the whole point of those. So the first thing I'm going to do with this, well, I'll go ahead and bring up the whiteboard in a second, but the first thing I'm going to do is I'm going to move this 16 minus x squared over to the other side. So I just have my y prime equals, because then I know what I need to do. Then I just need to integrate to get my y. All right, so let me jump over to the whiteboard. Just tried to use my pen instead of the stylus on my pad. That was beautiful this morning. All right, so if we move that over, what we're going to say is dy dx equals 1 over 16 minus x squared. And again, we're told y of 0 equals 6. All right, so what we're going to want to do, we're going to try to find y, is we need to integrate. Right? We got y prime equals. So let's see if we can get the integral of 1 over 16 minus x squared. Oh, okay. So at this point, we can do trig sub because of the difference of squares, but I totally wouldn't. I would actually do partial fractions on this thing. The 16 minus x squared, that factors, it's a difference of squares. So we have 4 minus x times 4 plus x. So we could set that up as a over 4 minus x plus b over 4 plus x. If you were to combine those, that's what the top would look like, and that equals 1. So now you could go ahead and plug in some values, and I think I'm gonna, well, not, let's go ahead and do this. So if we plug in, say, 4, we're gonna get 8a plus nothing equals 1. So a is gonna equal 1/8. If we plug in -4, we're gonna get no a's plus 8b's equal 1. So those are both the same. So this is 1/8 times the integral of 1 over 4 minus x plus 1 over 4 plus x. And then those just turn into natural logs. Right? We're going to get the natural log of 4 minus x divided by a -1 because of the u substitution. And then plus the natural log of 4 plus x. Right? But there's also a plus c I apologize. I need to close here. Then we have our plus c. And that's where this comes in. So now when we plug in our 0, we're going to get 6. So 6 is going to equal 1/8 negative natural log of 4 plus the natural log of 4 plus c. Oh, hey, look, those are equal to 0. That tells me my c is equal to 6. So there's my expression for y. So with initial value problems, just remember we integrate like normal, but then the initial value, that tells us how to find the exact value for c. All right, so.
Cool, I appreciate that. I
yeah.
For some reason, just hit a brick wall on those problems, and basically just, I don't know, it just didn't make sense to me, but this does, so appreciate it.
Sometimes that's it's one of those things that we saw a while ago and you kind of forget about, and all of a sudden it's like, wait a minute, it feels like a completely different problem, even though it's not really. So, all right, so there was the question from 3.3. So let's go look at 3.4. So we have a whole bunch from Lexi. So let's at least get them started, right? Because as you guys know, as you saw, partial fraction problems can take forever. And so if I actually were to do all 3 of these, we would run out of time today. There would be no more time for anything else. So I cannot do that. So we're going to at least get them set up so that we can kind of go in the right direction, okay? So let me just go ahead and write this one down. You all see it on the board, hopefully, or on the screen. All right, so let's go to the whiteboard for this one. All right, so we're integrating 13x plus 12 over 3x plus 2 times x plus 4. And I'm going to guess, and Alexi, you can correct me if I'm wrong. I'm going to guess that it's just the algebra. Yeah, like you just put in the chat, that's the hard part. Okay, so here's this guy. Now they already did us a favor. The denominator's factored already for us. So we can jump immediately to what these fractions are going to look like. The denominators are going to be the factors, 3x plus 2 and x plus 4. Since they're both linear, they're just going to get constants. So putting those together, if I were to add them into one fraction, this is what the top's going to look like. Because the first one is going to be multiplied by x plus 4 over x plus 4. Not a 9. That's a 4. And then the second one's going to be multiplied by 3x plus 2 over 3x plus 2. This is the last time I'm going to show this step because you all should be able to see how I'm doing that. I'm going to trust that you know how to add fractions. All right, so that's what the top's going to look like. And we know that that has to equal the other top, 13x plus 12. All right, so now I need to figure out a and b, and I'm going to use the same trick by plugging in some x values. I'm going to start with x equals minus 4. All right, when I plug that in, I'm going to get a times 0. 3 times minus 4 is minus 12, plus 2 is minus 10. So I get minus 10b. And then on the other side, I'm going to get negative 4 times 13 is negative 52, plus 12 is negative 40. So dividing by 10 gives me b equals 4. Okay, so that one's nice and fast. And then I have to pick another number to plug in. Now, normally, I would plug in the other 0, the other thing that makes a factor 0, which would be minus 2/3. I don't want to plug in minus 2/3. It's way too early for that nonsense. So instead, I'm going to plug in 0. That's going to give me 4a plus 2b equals 12. And I already know what b is, right? B was 4. So that's a pretty quick a equals 1. Okay, so that tells me that this is the same as integrating 1 over 3x plus 2 plus 4 over x plus 4 dx. And at this point, I'll let you go. It's going to give you some natural logs.
So I guess my question is, does the first one make a natural log too? Even though it's not there? It is?
Oh yeah, absolutely. Do a u substitution. If you integrate 1 over 3x plus 2, you let u equal 3x plus 2. So du is 3 dx. This turns into the integral of 1/3 du over u, which is 1/3 natural log of u, which is 1/3 natural log of 3x plus 2. So fun fact, anytime you've got a linear denominator, just the linear with a constant on top, it's always going to be a natural log. It won't necessarily be just the natural log of this. Like you notice that there's a 1/3, but that's because of chain rule with differentiation. All right, so cool for that one. So let's go see what fun number 15 gives us. Oh man, that was nice of them to have it factored again. Look at that, saving us steps left and right. Okay, let me go ahead and write this down. And we'll go to the whiteboard. All right, so again, super nice of them to have this already factored for us. Let's go, we got x squared plus 3 and x minus 6. Okay, so our fractions are going to be, one of them's got x squared plus 3. The other one's got x minus 6. So this first one, since it's a quadratic factor, tells me I need a linear piece on top. So ax plus b. And then the other one is a linear factor, so it just gets a constant. So if I were to add those together and get a common denominator, it's going to look like this. And so that top is going to equal the top that we started with. All right, let's start plugging numbers in. So the first one I'm going to plug in is x equals 6, because that makes this guy 0. So when I plug in 6, this first bit is all gone. I'm left with 36 plus 3, which is 39c. And on the other side, let's see, 6 squared is 36 times 3 is 252, I think. Plus 3 is 255 minus 138. Oh my goodness. I totally don't know where I am anymore. Yeah, equals some number we can solve for C. If somebody wants to do that, my brain is not working that fast this morning. Like seriously, if somebody can calculate that and type it in the chat box, that would be much appreciated. So we're going to get a value for C, which is cool. But now we need to get the others. And there are no other good numbers to plug in. So I'm going to plug in 0 for my next one. If I plug in 0, the AX is gone. This becomes a -6. So I get -6B. This one I get plus 3C. And then that equals 3. So once we have this value for C, we can plug that in here. That will get us our value for B. And then we need to plug something else in. I'll just plug in 1, because I think that'll be nice and easy. So I'm going to get A plus B times -5. So -5A minus 5B plus 4C. And I get 7 plus 3 is 10, minus 23 is -13. So again, from these, I'm going to have my C equals my B equals, which then gives me an A equals. Seriously, nobody did that for me? 7 times 36 minus 23 times 6 plus 3. Oh, my calculator's not handy. All right, well, since you guys didn't give me a value for C, you're going to be on your own. Oh, there it is. There's no way it's -573. I mean, I can tell you that much, because this is on the order of 100. And that's on the order of 200 something. It should be a positive number.
I guess my question is more like, what do you do if you can't do it by plugging in? Do you have to do it the other way that you showed us Monday?
You can always do it by plugging in.
Oh, you can?
You can always do it by plugging in. It will potentially give you a system of equations.
Yeah, because I kept getting like all the letters.
Okay, so you have 3 equations with 3 unknowns. You have to solve that system by, remember the good old like substitution and elimination stuff?
Oh yeah. Oh, you can do that. Like you can set them equal.
Yeah, that's totally what you do when you have things that don't turn out to just give you like C equals a number and so on. So
okay, then that makes sense. I think I can do it.
Yep. Okay, so again, whatever. That one's on you guys. All right, so then lastly, let's just get this other one set up. Number 19. Okay, so, oh, hey, look, it's an initial value problem. Well, that's cool. So same deal as before with the one that Rigney asked about from the other section. Once we get our antiderivative, we have our C in there. Well, we're going to plug in this case, we're going to plug in 7 and set it equal to 0. This little bit here where it says T is greater than 6, that's a total CYA statement. That's the math lawyer coming out to make sure that there isn't anything funky. There's an asymptote with this function, and that's why they gave us that. But let's go ahead and look at this guy real quick. Back to black. All right, so we had t squared minus 7t plus 6 times dx dt was equal to 1. So I would start exactly the same way we did with the other one, which is get my dx dt by itself, because then I can just integrate, right? So x is going to be the integral of this thing. So this is going to suggest using partial fractions. This time we do have to factor. They weren't nice. So t squared minus 7t plus 6. hopefully you see that's one of the quick ones. Two numbers that multiply to 6 and add up to -7 are -1 and -6. So this thing, when we break it apart, both of those are linear factors, so they both just have a constant. So we get a times t minus 6 plus b times t minus 1, and that's going to have to equal 1. All right, so plug in numbers. How about we start with t equals 6? Makes the a go away. I get 5b equals 1, or b is 1/5. And then I'll plug in t equals 1. Gives me minus 5a equals 1, or a is minus 1/5. And from here, you know what to do. They're both going to give you natural logs. Again, there's going to be the 1/5 out front, whatever. But then with that plus c, again, you're going to plug 7 in for your t value, and it has to equal 0. All right, so algebra. Nothing but algebra when it comes to doing these, and lots of it, right? A lot of things you have to do. You have to be able to factor. You potentially have to solve systems of equations. Yeah, there's a lot. All righty. Yep, all the fun. All algebra all the time. All fun all the time. Okay, cool. So there was a good little review about your partial fractions. Expect log forms a lot with those integrals. You'll also get inverse tangent a lot from the quadratics. Sometimes you have to do some completing a square, other fun algebra as well. Okay, so we're going to get away from algebra for a little bit. We're going to get back to calculus. But I want to show you these things called improper integrals, and how we deal with those. So I will be right back with you. I'm going to hop up to the whiteboard. All right, so improper integrals. These are ones that have problems with our bounds. Okay, they are integrals with bounds. They are definite integrals, but they have bounds that lead to issues. All right, and really there are two types of these. The first type, we can call them type 1 and 2. These aren't like the actual names of them, but the first type, this is one where one or more of the bounds is infinite. So an example, I'll do an example over here. An example would be something like the integral from 1 to infinity of, say, 1 over x cubed. Okay, so this is an improper integral because there's an infinite bound. And infinite bounds, of course, there are issues with infinity always. But think about what does this mean, right? This means, okay, we're finding the area under this curve, area under 1 over x cubed, as we go from 1 forever. There is no place where we terminate anymore. This would be, now we're just going to keep doing. All right, that seems weird, and it seems like it might be a problem. So you can definitely see why we need to talk about it. All right, so that's the first type of improper integral. But then the second type is going to be where one or more of the bounds I'm going to put here leads to the function being undefined. So this is going to be a situation where we try to integrate, but integrate something that we can't actually plug in. All right. So an example of that would be, I'm going to use the same function here, 1 over x cubed. But what if we did, say, the integral from 0 to 2 of 1 over x cubed dx? So think about what's going on there. All right, so we're integrating from 0 to 2, no big deal. We got nice finite bounds. But look at what happens as we get closer and closer to 0. 1 over x cubed, that starts getting really big. And so if we started to try to, find the area under that curve, or we're adding rectangles, we start adding bigger and bigger and bigger rectangles. Right? And in fact, 0 is even a problem because that function is not even defined at 0. There is no point at which we end. So with improper integrals, like the big idea here, the improper integrals lead to a problem with one of the bounds. And these problems are infinite. We're either going to infinity, or the values we're approaching as we get to these points is infinite. Okay, so improper integral. So the question is, how do we deal with them? Well, we're going to be tricky. Let's start with this type, the first type where the bounds are infinite. And let's think about this 1 over x cubed. All right, so if I were to draw the graph of 1 over x cubed, it looks something like this. But I'm just going to do the part that's in the positive area because I don't really care about what's going on over here in the negative. But 1 over x cubed is one of those kind of butterfly-ish kind of functions. Looks like this. And again, what we're being asked to do is to find the area under this curve from 1 to infinity. And I know what your probably initial thought is. Well, it's got to be infinite. As we move out, we just include more and more area. So this thing must be infinite. But let me remind you of another situation where you probably thought, oh, this result must be infinite, where it wasn't. You remember doing something like this, the old 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... forever?
You mean Riemann sum?
Okay, so not the, well, not exactly a Riemann sum, but just an infinite sum. This was an infinite geometric sum. Hopefully you remember that that actually is a number. It's just plain old 1. So there are times that you can add forever and still get finite numbers. There are times when you add forever and you don't get finite numbers, right? Like just think about adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever. That's going to blow up. So there are certain infinite sums that give you finite values, and there are some that don't. Okay, so you have seen, or should have seen, situations where like continually adding stuff still led to finite values. Now, if you think about what we're really doing here, we're adding rectangles, right? Remember that was how we did integral before, or how we thought about integral. So if we're adding up a whole bunch of things, well, there's the possibility that it actually is a finite number. Okay, so that's the first thing that's a little bit funky. When we have integrals like this, we might get a number, a finite number, or we might not. It's just going to depend on what the function is and what the bounds are. Really what the function. Okay, so improper integrals, sometimes we're not going to get finite numbers. So we have to have some terminology for this. If, for one of these, the integral is a finite number, we say that it converges. Okay, so let me just write this. If we get a finite answer, we say the integral converges. Otherwise, we say it diverges. Again, if you remember your sums, your infinite sum stuff, those were terms that we used there as well. So convergement, something like this, that we got a nice number for it. Diverge means it blew up. Okay, so when we have improper integrals, we'll use these terms a lot, converge or diverge, depending upon where we are, what the result is. Okay, so yay, we already have to worry about this. Sometimes we get numbers, sometimes we don't. But then the question is, all right, well, let's say it does converge. How do we get that value? Or how do we know whether it converges or diverges? So this is where we're going to pull a math trick. This is a total mathematician trick. Instead of actually integrating, say, from 1 to infinity, I'm not going to integrate to infinity. Infinity is a problem, right? Like, I don't know how to deal with a bound that's not really a bound. So instead, here's what we're going to do. Instead of doing 0 to infinity, because I have no idea what to do there, what if I instead integrated from, say, 0 to b? So I'm not going to go to infinity. I'm just going to go to b, somewhere out here, somewhere out along the ways. There's going to be a number b. If there's a number b, can you do this integral?
Yeah, it would be definite.
Yeah, then it's a definite integral. We know what to do. Use the fundamental theorem of calculus. We find the antiderivative. We plug in b and 0, and we're done. Okay, so I can pick any b out here, and I can do that integral. Right? You give me a number. You say 1 to a million. Okay, no problem. Plug in a million. Plug in 1. Good. All right, so I can go to any value I want. But then here's the math trick. I'm going to say, well, what if I just let that b get bigger and bigger and bigger and bigger? In essence, what if I take a limit as b goes to infinity? Oh, sneaky little math guys. All right, so we're not actually plugging in infinity. We're plugging in b. But then we're going to let b go to infinity. And we're going to see what happens there. So remember all that limit stuff from forever ago? Yep, it's coming back. We get to use the limits again. All right, so check this out. Watch how this works. Okay, so the 1 over x cubed. We'll go ahead and keep running this one up here. We'll need a little more space. All right, so we're going to get the limit as b goes to infinity. But let's think about 1 over x cubed. That's x to the minus 3. So if we anti-differentiate that, you're going to get minus 1 over x squared. Minus 1 over 2x squared. So that's the antiderivative of 1 over x cubed. Except we weren't doing 0 to 3. Hold on. Or 0, we're doing 1 to infinity. 0 to infinity is a whole nother issue. Okay, so we're integrating from 1 to infinity. Instead, we integrate 1 to b, because we know how to do that. So let's plug in those bounds. So we're still going to limit as b goes to infinity, but when I plug in b, I get minus 1 over 2b squared. When I plug in 1, I get negative 1/2, but I'm subtracting it. So this is the result of the integral. It's minus 1 over 2b squared plus 1/2. So if you just want to know the area under this curve from 1 to any spot out here, that's what it is. You plug in the b value. So if you want to know the integral from 1 to 10, plug in 10. Integral from 1 to a million, plug in a million. Okay, so now let's take the limit. So what's going to happen to this first part? As b gets really big, what happens to the 1 over 2b squared? Uh-oh, infinite limits. That's actually going to go to 0. Right? If b is large, squaring it makes it even bigger. Dividing it into 1 makes that really, really small. The 1/2, of course, just stays 1/2 because there is no b. And so what we end up with is 1/2. So this integral, the integral from 1 to infinity of 1 over x cubed dx, actually converges. It's a convergent integral. And the value that it takes on is 1/2. So believe it or not, there's not an infinite amount of area under this curve. It's finite, well, at least from 1 to infinity. It's actually 1/2 is how big that is. Okay, so this is the approach. This is how we deal with these weird infinite limits, is we don't integrate to infinity, we integrate to b, but then we let b go to infinity. All right, so let me show you another example. Let's look at this one. Let's do the integral from 0 to infinity of x e to the minus x dx. All right, so again, we've got an infinite limit, which means we need to, or an infinite bound, so we need to do a limit. So we're going to do a limit as b goes to infinity of the integral from 0 to b x e to the minus x dx. Because this we can do. All right, so let's see if we can do that integral. So looking at x e to the minus x, what technique do you want to use? What should we use to integrate x e to the minus x?
Integration by parts.
All right, so we're going to do integration by parts, beauty. So we'll let u equal x. U is going to equal x. dv is going to be e to the minus x dx. right? Liate. So then du is dx, v is minus e to the minus x. So we get u times v, so minus x e to the minus x, minus integral of v du, that's going to be plus the integral of e to the minus x dx. And that one's easy enough to do. That's again just another minus e to the minus x. So we get the limit as b goes to infinity of minus x e to the minus x minus e to the minus x, evaluated at 0 and at b. All right, so that's the antiderivative. So now we plug in b and 0. So we're going to get the limit as b goes to infinity of, well, when I plug in b, I'm going to get minus b e to the minus b minus e to the minus b. And when I plug in 0, I get minus 1. So subtracting the minus 1 is 1. All right, so all that stuff that's in the parentheses, that's actually the integral from 0 to b. That's the value we're going to get if we just cut ourselves off. But now we need to see what happens as we go to infinity. Now, to help us see that, I'm going to rewrite these things real quick with the minus b powers. I'm going to drop them to the denominators. Because I think that will help us a little bit. So let's think about the limit as b goes to infinity. So the 1, of course, that's going to go to 1. The 1 over e to the b. So b gets really big, e to the b gets super big. And so 1 over that goes to 0. So that piece is going to drop out. Right, maybe plug in infinity, I get 1 over infinity, which is 0. Okay, so what about this first one? What happens as b goes to infinity? If you plug in infinity, you get infinity over infinity. That should have just totally set off an alarm bell. What do you do when you get infinity over infinity? It could be 1, Bruno.
There's a method, I can't remember the name of it, but you apply a method to that. L'Hopital, there it is.
Yes, the L'Hopital's rule. Good. Okay, so this is one, infinity over infinity could be anything. It literally can be any value. It's what we call an indeterminate form. So what we have to do is L'Hopital's rule. And L'Hopital's rule, that's one where we differentiate the top and we differentiate the bottom. And then we take the limit of that. So let me remind you L'Hopital's rule here. Come back onto this side. All right, so we're going to apply L'Hopital's rule to b over e to the b. I'm going to apply L'Hopital's rule. So we got the limit as b goes to infinity of b over e to the b. So what we do, we're still going to take a limit as b goes to infinity, but we differentiate the top and the bottom. So the derivative of b is going to be 1. The derivative of e to the b is e to the b. Right, so again, all I did was I differentiated as I went down. If you don't like the b's, make them x's. That's totally fine, if that helps you see it. But same kind of deal. So now I can see that when I plug this in, I get 1 over infinity, which tells me that that's actually 0. So this form of infinity over infinity actually equals 0. Okay, so we've got 0 minus 0 plus 1, which gives us 1. So this integral from 0 to infinity of x e to the minus x dx is actually equal to 1. Ta-da. All right. So this is another one that converges. It's got finite area, even though it's got infinite bounds. Okay, so be ready for L'Hopital's rule. L'Hopital's rule is going to come up with these quite frequently. So go back and review that if you haven't seen it in a while or you're not really sure how it works, because you're going to make a mistake. All right, so I've shown you a couple that converge. I want to show you one that doesn't. I want to show you one that diverges, just so you can see that not everything is nice, all work out. All right, so how about we look at this guy? Super easy one, super easy function. Let's just look at sine of x. And let's integrate that from 0 to infinity. All right, so again, let's do the same trick. We'll take a limit as b goes to infinity of the integral from 0 to b sine x dx. So the integral of sine is negative cosine. And evaluate that at 0 and b. So that's going to give us negative cosine of b and then when I plug in 0, I get 1. I'm subtracting a negative 1, which is plus 1. So we just need to take the limit as b goes to infinity of minus cosine of b plus 1. All right, so the plus 1, no big deal. That just goes to 1. So what about negative cosine of b, or just cosine of b? What happens to cosine of b as we go really far out?
The same thing over and over again.
Okay, so it's going to repeat, right? Because it's cyclical. Is there a specific value that we approach? And the answer to that is no, right? It bounces back and forth between plus and minus 1. So this one, the limit as b goes to infinity of cosine of b, this doesn't exist. Because there isn't a number that we approach. So since this limit doesn't exist, this integral doesn't exist. And so what we say here just diverges. This is a nonsense statement. I mean, you can tell me integrate sine of x from 0 to infinity. But I'm just going to say it, no, You can't. It's not possible. It's definitely possible to stop it at any place and evaluate. But if you then say, go ahead and take this to infinity, I'm going to say, nope, can't do it. Doesn't work. So sometimes you get divergent improper integrals because the limit doesn't exist. Okay. For some of you, you're probably going to need to go back and look at limits. You have to remind yourself how they work. Because again, if you're not comfortable with limits, you can't do improper integral. Now, this one should have made sense at the very start that it was divergent. Like we shouldn't have had to do the math on it. Because think about the graph of sine of x from 0 to infinity. Okay, so of course, sine of x does something like this. Right, and just continues forever. But think about what's happening as we continue on. We're always adding on more stuff or subtracting value because we're down below, or adding value or subtracting value, but it never goes away. It never gets to a point where we're adding virtually nothing. Like compare this to the 1 over x cubed, right? The 1 over x cubed that did this. As we keep adding rectangles, those rectangles get super small for 1 over x cubed. And in fact, that's something that you know for sure. All right. If the function doesn't drop to 0, it's going to be a divergent integral. Okay, for these first type. We'll worry about the other ones next time. But for this first type where we've got an infinite bound, if that function isn't dropping to 0 as you go to infinity, it's gonna be divergent integral. All right, so I'll even write that statement up here. If I put it on the board, it's gotta be true. All right, but if the limit as x goes to infinity of f of x does not equal 0, then the integral from a to infinity of f of x will be divergent. Okay, so if that function doesn't drop to 0, you know right away this is going to be a divergent integral. Because the area that I'm adding, or the signed area, however you want to think about it, the values that I'm adding, don't drop off. They don't go to 0. Okay, but this statement, I want to be very clear about this, very clear. The converse is not true. Just because the limit does go to 0 does not mean that it converges. All right, those you never know. Okay, so here's that if the limit as x goes to infinity of f of x does equal 0, you have no idea if the integral converges or diverges. You can't just look at that and go, oh, it converges, or oh, it diverges, because it depends. Let me just show you one real quick that diverges. So you've already seen, a couple that converge, the 1 over x cubed, and then the x e to the minus x. But check this one out. This is super easy to do. Let's just look at 1 over x. And we're going to go from 1 to infinity. So you know what it looks like. You know that it does drop to 0. But watch what happens when we do this integral. So we're going to do the limit as b goes to infinity. Integral from 1 to b. Well, 1 over x, its integral is natural log. All right, so I put in the values here. So we're going to take the limit as b goes to infinity of natural log of b minus the natural log of 1, which is 0. All right, so what happens to natural log is we plug in bigger and bigger and bigger numbers. Well, they get bigger and bigger and bigger and bigger. So this one diverges. So even though what we're adding is getting smaller, it still ends up adding up to infinity. So basically, it's not getting smaller quickly enough. Yeah, infinity's weird. Infinity's weird. You can add an infinite amount of very small things and still get an infinite value. But you can also add an infinite amount of small things and get a finite value. If that hurts your brain, it probably should. It's kind of a weird thing. But the moral of the story is you can add forever and get finite numbers. We've already seen that. So that means with integrals, you can integrate forever and still get finite numbers sometimes. And the only way we're going to know is by going through the process, by taking an infinite limit. Oh, yay. All right, so there's your first little taste of improper integrals. So on Monday, we'll continue this conversation. We'll do a couple more like this and then look at that other type. Just so you guys know, I am going to change that homework to be due not Monday night, this coming Monday night, but the following Monday night. And also, I want to let you know that we are skipping section 3.6, I think it is. It's whatever the one on, like, it's called numerical integration or whatever. I have subsequently deleted that homework, so it's no longer in there. And I apologize to Eris, who's the only one who actually had started it at this point. So that thing is gone. We're not going to talk about that. It's computational stuff that, to be quite frankly, is boring, and it's really only useful for people that are going to be going into applied mathematics. And if you're one of those people, you'll be able to pick it up. I'm quite confident. Anyway, so on Monday, we'll go ahead and take care of these improper integrals, and then start moving into the last chapter of the textbook, or that we're going to do this quarter, chapter 4. All right, so with that, I'm going to wish you all a very happy weekend, and I will see you all on Monday.